In the last video we introduced the concept of work, and we said it was force times distance. In that case though, we were only considering constant forces. Here we're going to look at what happens when that force is changing, and you guessed it, we have to use a little bit of calculus to deal with it. It's fun. Before we jump into that though, a more succinct way of writing the equation for work is the scalar or the dot product, which requires vector notation here, because earlier we said that work is the force, the component of force in the direction of the displacement, which is the same as FD cosine theta, where theta is the angle between the force and the displacement, and you can write that as the vector dot product F dot D. So moving right along, if we have a varying force, essentially what you have to do is take force times d cosine theta for each different force that you have, and if your force is continually changing, you could approximate it by doing some d that's a delta L here, and then summing over all of those segments. But what we really want is to find the exact area under that curve. As you know, that's the limit as that little step size goes to 0, and this becomes an integral. So here is a nice robust formula for work, again using our dot product notation, but if you prefer to do it this way you can. So F dot dl integral from A to B, and that will give you the work done, and eventually we'll see that this is also equal to the the energy stored or removed, depending on your perspective. Okay, let's look at an example of doing that. If we have a spring force is not constant. As you stretch or compress that spring, the force is constantly changing. It changes linearly, so this would be our graph of the spring force as a function of the displacement here. And so if we use that new definition, that the work done in stretching the spring is F dx, and then if we plug in for F, then we've got Kx dx, and then this is a pretty simple integral. K is the spring stiffness constant, so that's constant, and it comes out. We end up with Kx squared over 2, and this you might recognize as the amount of elastic energy stored in a spring, but that is also equal to the work done stretching or compressing a spring, because those two ideas are equivalent, that the work done is the amount of energy you store. So there's an example of how you can get that nicely from that expression for work. So let's look at doing some calculations with springs. We want to know the work required to stretch it 3 centimeters. The maximum force is 75 newtons. So we need to know K, and we can just plug into F equals Kx. This is Hooke's law, by the way. And the maximum force occurs at the maximum stretch. So we can use this and solve for K, 0.03 meters. Divide that, and you get a big fat K of 2,500 newtons per meter. Then we could either just jump to that expression that we had already, 1/2 Kx squared, and plug in there. If you really wanted, you could kind of redo the calculation and say the work is K times the integral of x dx from 0 to 0.03, but that is just going to give you this same expression, right? You're going to get 1/2 Kx squared evaluated from 0 to 0.03, same thing. You end up with 1.125 joules of energy stored in that spring. If instead you're compressing it, well, this equation here, the x applies to compressed or stretched, as it showed previously here. X can be that way or that way. So it's going to be an identical calculation. No need to redo something where we already know the answer. So you get just as much energy to compress it the same length. This is assuming we have a nice, well-behaved spring. In reality, springs can be non-linear and more complicated, but for most of our problems they'll be nice and linear and obey Hooke's laws. Alright, let's look at something a little bit more complex. We've got some camera on a robot arm where the force exerted on the arm is given by some strange function here. And we want to know the work done by the motor to move this arm from a position of 0.01 to 0.05 meters. So we're going to use work equals FDX and from 0.01 to 0.05, and then we plug in this thing. Now the F naught and the X naught are just constants of 2 and 0.007, so we can pull the F naught out of the integral. That's going to be a 2 out there, 0.01 to 0.05, and then we're going to have 1 plus, now we're going to have 1/6 over 0.007 squared, x squared, 0.007 squared, that whole thing dx. Okay, now we take the integral and you do each term separately. So that 2 is out front. I'll put a big fat bracket here. That 1 just becomes an x. I'm going to plug this stuff in later, so I'm just going to call all of this stuff a because I don't want to write it a bunch of times. So I'm going to have a x cubed over 3. And then we evaluate that from 0.01 to 0.05. And for some of you that might be a little rusty on evaluating integrals, so you plug in this value here for all of your x's plus a over 3 times 0.05 cubed. And then you subtract the whole thing again with 0.01 plugged in. I guess we could have factored that 2 out and just kind of left it out front. But anyway, 0.01 plus a over 3 times 0.01 cubed. That a again is this nasty stuff. You plug in your numbers and you'll get 0.3834 minus 0.02227. Now these numbers are rounded a bit, but when I actually did the subtraction in my calculator, I kept all the digits that my calculator could. I don't want to encourage intermediate rounding. Anyway, this works out to be 0.36 joules. So a little bit of calculus occasionally, but hopefully not too bad. Alright, see you next time.